interpreting a reaction energy diagram. Okay, so here's a reaction energy diagram. We've looked at these before back in Gen Chem 1. And now, as well as seeing the energy level of the reactants, which in this case is A and B, and the products, which in this case is C and D, we have this big hump in the middle, which now we know from the Arrhenius equation is the activation energy, which represents the things that have to align in order for the reactants to actually react with each other. Okay, are they in the correct orientation? Do they have sufficient energy to start forming that partial transition state where one bond is starting to break and the other bond is starting to form? So activation energy is larger usually than the delta H for the reaction. So remember, delta H is our enthalpy change for our reaction, and it is a state function. So to work out the change in enthalpy, which we always use a triangle sign delta for, it's going to be the enthalpy for the final state, which is of course our products, minus the enthalpy for our initial state, which for a chemical reaction is always going to be the reactant. So let's just draw my little delta in there. Okay, so we're asked first of all, what is the heat of reaction? So we're going to look for where the initial and final states are. I guess I can just use, so this is our initial state. So our initial enthalpy, and then our final state will be up here for our products, and we're just going to do the read off the plot for our final state of our products minus our initial state for our reactants. So we are looking in terms of an energy difference from this level to here. That is going to correspond to delta H. Let's draw my little delta again, delta H. So that we can see graphically is an increase in enthalpy. So an increase in enthalpy means that reaction is having to absorb energy. And remember, we defined this back in Gen Chem 1, that a positive value for delta H is what we'd call endothermic reaction. So it's absorbing heat, absorbs heat. And then a negative value for our delta H of reaction would be an exothermic reaction, which releases heat. Let me just do a quick copy paste. Exo releases. All right, so we draw a little delta sign. Here we go, delta, delta, delta. Really wish I had a little triangle stamp for there, but you know, them's the breaks. So let's go ahead and actually work out the heat of reaction then. So our final state of our products, if I read off the plot, that to me looks like it's about 150 kilojoules per mole. So my delta H is going to be 150 kilojoules per mole minus my initial state, which looking at this plot looks like it's 50 kilojoules per mole. So 150 minus 50 is going to give me a delta H of just 100 kilojoules per mole. And of course, that is a positive value. So that is telling me that the reaction is absorbing heat. It is endothermic. Of course, if my arrow was pointing the other way, if the reactants were at a higher energy than the products, then that would be an exothermic reaction. But we're going to click endo. Can I determine the activation energy? So the activation energy, let's change color, is this hump all the way up here, okay? So there's quite a big hump that you've got to get over to before we can form those products. So to measure the absolute activation energy, you've got to go from that initial state, which is the reactants, to however high that activation energy is. So looking at this, yes, we can determine it, and it is going to be 400 kilojoules minus whatever energy we started at, which was, looks like 50 kilojoules. So that is going to be 350 kilojoules. Okay, that energy is being absorbed. The arrow is going up. Remember, going up is absorption. Going to a higher energy state and going down is going to be release of energy. So that would be a negative number. Okay, so yes, we can determine the activation energy. Yes, it's 350 kilojoules per mole. Can you determine the activation energy of the reverse reaction? Well, yes, we can, because the reverse reaction, let's change color, would be reactants C plus D forming products A plus B. So we are going to just travel the opposite direction along this plot. So give you a little sort of visual guide here, we would be starting off here, and then going around here, dab, da, dab, da, dab, da, dab, da, dab, like so. So if we are going to measure the activation energy for the reverse reaction, our products, C and D, are at a higher energy than our initial reactants, A plus B, for the going the right way equation, the forwards reaction. So to work out the activation energy, we only have to go from the energy level that C and D are at. So let's go ahead and do that. So again, our peak of our activation energy is still 400 kilojoules, but we are already at what looks like 150 kilojoules of energy there for the products. So 450 minus 150 would give me 250 kilojoules for the activation energy of the reverse reaction. So another thing, while we're looking at this, the reverse reaction would in fact be an exothermic reaction, because if you look, the energy level for C plus D, which are now our reactants, is higher than A plus B. So this reaction would be releasing 100 kilojoules per mole of heat if it occurred in the reverse direction. So that's the nice thing about these energy diagrams, that you can actually tell about the forward reaction, and you can also read the reverse reaction in them as well.